So our first speaker will be addressing tree rings, a record of past flow with implications for the future, and it is Connie A. Woodhouse, who is an associate professor in geography and regional development at the University of Arizona. Connie.
Thank you very much, and I'd like to thank the organizers for inviting me. This has been a really interesting and stimulating symposium so far, and I'm really looking forward to the talks, the rest of the talks today. Yesterday morning, Patty Limerick started off the symposium with a really interesting talk, and one of the things that she mentioned was the top 10 list of things we could be smug about. And number one on that list was the allocation of the Colorado River resources that were made in the 1922 compact were based on a record of flow that was quite high compared to the gauge record that we see today. So I'm going to be addressing that. We heard a few references to tree rings yesterday, and I'll be going into more detail about those records and how they can be used not only to place that wet period, the early 20th century wet period, into a long-term context, but also how the full gauge record looks like compared to a longer-term record. Before I begin, I'd like to also acknowledge my collaborators with whom I could not have done this work. These include a number of people, but in particular Jeff Lucas at the University of Colorado, Robin Webb at NOAA in Boulder, Dave Miko at University of Arizona, and Steve Gray, who's now at the University of Wyoming, and also support through the Western Water Assessment, a NOAA-supported program through the University of Colorado. So to start with, let's do a little bit of an overview. The first thing I'll talk about briefly is the Colorado River gauge record and some of the early reconstructions of streamflow from tree rings. Then I'll talk about the reliability of the reconstructions. I'll tell you a little bit about how these reconstructions are generated so you can assess the robustness of these reconstructions. I'll then talk about some recent reconstructions of streamflow that we've done, placing the gauge record in the context of the past 500 years and briefly the past 1,200 years. I'll talk about the implications of these extended records, and finally address the relevance of these records of the past in the face of a changing climate. So first of all, of course, the Colorado River Compact signed in 1922 was based on this assumed flow of, well, it varies according to who you talk to, but it's, I'm calling it 16.4 million acre-feet a year. Let's see if I've got, this is the pointer, yeah. So here's the gauge record of stream flow. This is the natural flow, so we've got the effects of diversions and evaporations and reservoirs removed. The light line, which you can't see too well, are the annual values, the water year values. The dark line is smooth of the 5-year filter from 1869 to 2003. I believe the compact was based on data from 1899 to 1920, and the average, and that was actually on the gauge at Yuma, the average for that period at least Ferry is 16.4. The long-term average is shown here. It's about 15 million acre-feet. The compact was based on, as I said, this average of about 16.4. So you can see there's a difference there. And the question that comes up then is how representative is this period of the record? It's certainly unusual in the context of this gauge record, but what about longer periods of time? The first reconstruction of stream flow of the Colorado River at least Ferry was done by Chuck Stockton and Gordon Jacoby in 1976. And here's their record from 1564 to 1964. There's the compact, the time of the compact drafting. There's that period of high flow. And in this record, we can look back and see, indeed, it was unusual in the context of this record. This is the one period that looks like it might be close to that. This record also showed a number of droughts that were more severe and sustained than anything we see in the record up to 1962, including this very sustained period of drought in the late 16th century. Stockton and Jacoby in their report said the timing of the drafting of the compact was an unfortunate event in that it did not occur during a representative period of flow. And the general picture of a collision between water demand and supply in the upper Colorado River Basin in the not-too-distant future is all too apparent. Well, following their report in 1976, we had a very dry winter, 1976-77. But after that, the next couple of decades, except for a few years here and there, were relatively wetter, at least average. And it wasn't until the recent drought where this not-too-distant future picture of collision started to emerge. And we're looking at this point, the water supply and demand coming into conflict. There were several other studies that developed reconstructions of streamflow following the work of Stockton and Jacoby, Michelson et al. In 1990, and Hidalgo et al. In 2000. The reconstructions varied in some respects, but they both showed that the early 20th century records of flow were unusually high in the context of the past centuries, and that droughts prior to the 20th century had been more severe and sustained than anything in the gauge record. Now, these three studies were all based on treeing data that were limited in length coming up to into the 1960s. So they all ended in the 1960s, which at this point we could potentially get another 40 years of data by going out and recollecting the data. So a few years ago, some colleagues and I started a concerted effort to update these chronologies and to collect new chronologies. And we've now developed some reconstructions that are updated to the late 1990s. So I'm going to be talking a little bit about those. But before I do, I want to talk a little bit about the methods that we use for reconstructing streamflow from tree rings, and to give you an idea of how this is done, the quality of the reconstructions, and how good of a job they do. So to start with, how is tree growth related to climate? Well, variations in ring widths reflect the conditions that influence tree growth. So here in this little cartoon, we have a cross-section of a conifer. Here's the center of the tree, the pith, the bark, and here are the annual ring widths. And you can see they vary in width. And typically, especially in the arid west, climate is a primary influence on growth. So the variations in widths are reflecting climate, and the time series of the widths that can then be used as a proxy for past climate. If we're looking for trees that would be good candidates for reconstructing moisture variability, things like streamflow, precipitation, and drought, there's certain things we can do to make sure the trees that we collect contain that signal in their ring widths. First of all, we know that particular species, Douglas fir, pinyon pine, and ponderosa pine, these tend to be lower elevation conifers, are more sensitive to variations in moisture. So in their tree rings, narrow rings indicate dry years, and wide rings indicate wet years. And also, if we look for stands of these species in areas where there's not much soil, where there's steep slopes, where they're open grown, we can enhance that climate signal. So those are the kind of trees that we target for collection. What we're looking for is this kind of a relationship. What I've got graphed here is the precipitation, annual precipitation for western Colorado in blue. And this is one tree ring series from one tree. These are just the raw measurements. And you can see how well they correspond to the variations in annual precipitation in this area. This is one tree up on Grand Mesa, a pinyon pine. The correlation between the two is about 0.7. So it's a very close association without just one tree. And we don't look at just one tree, we look at multiple trees, as I'll explain. So I'm showing you that tree growth from these species and these sites is highly correlated with precipitation. What about streamflow? I've just said that we collect the trees that are up on the side here. We don't collect the trees that are down here right in the river. Those trees are going to have their roots in the water table. They're not going to be sensitive to variations in moisture. So what we're getting is a rather indirect relationship between annual streamflow and tree growth. What we're seeing is that ring widths and streamflow both integrate the effects of precipitation and evapotranspiration as mediated by the soil over the course of the water year. And in particular, winter snowpack is quite important for both variables. Winter snowpack has a great bearing on annual streamflow, and winter snowpack, it turns out, conditions the soil. So at the beginning of the growing season, the amount of snowpack that fell over the winter has a lot to do with how much soil moisture there is, which really has a great bearing on the tree growth during the summer growing season. So it's an indirect relationship, and it's linked by regional climate, but it's a very robust relationship. So how do we sample trees? This is my research assistant, Jeff Lucas. He's coring a tree. He's using an increment bore, which is a hollow shaft of steel with a sharpened bit on one end and a handle at the other. He's extracting a core, which is about 1/4 inch in diameter. We generally sample about 20 trees per site and about 2 trees per core. We take those samples back to the lab, sand them down, and then we do a process called cross-dating, in which we don't just count the rings, but we actually match the ring width patterns from tree to tree to make sure that we have exact calendar year dates for each ring. Once they're all dated, they're measured using a system that looks like this, and then they're averaged together into site tree ring chronologies. And these tree ring chronologies are then the units that we use for reconstructing streamflow. So this map shows a lot of the chronologies that we've collected in the Colorado River Basin and surrounding areas. These little triangles are all tree and chronologies that are significantly correlated with annual flow at Lee's Ferry. And you can see they're distributed about the basin, but they're also on the other side, on the east side of the Continental Divide. And again, that's because the relationship between tree growth and stream flow is linked by regional climate, and primarily, or most strongly, by winter precipitation. So you can envision winter storms coming across the basin. They don't stop at the Continental Divide, of course. They continue to dump snow on the east side, so that's why we have that relationship. These are some of the sites that we've collected from. The chronologies with the red circles around them were the ones that ended up being important in our estimations of Colorado River at Lee's Ferry. And the way that we develop these reconstructions is we calibrate the tree chronologies with the Lee's Ferry gauge record for the common period of time, 1906 to 1995 in this case. We use some flavor of a multiple linear regression technique, a statistical technique, to come up with a regression equation. And those 7 chronologies that were circled in the previous slide were the chronologies that entered into this regression and made up the equation. And from the equation, we can generate a time series that we can compare with the gauge record. So the gauge record is in blue here. The reconstruction is in green. And you can see that it's a pretty good match. We're explaining about 81% of the variance in the gauge record. It's not perfect, but this is about as good as we do with tree rings. We're not explaining the balance of the variance. So we have some error, some uncertainty in the reconstruction, which you might expect since we're dealing with tree rings. And they're all responding to things, some non-climatic factors as well as climatic factors. So once we have this model, we go through a number of processes to evaluate the reconstruction. Once we're happy with that, we go ahead and take that regression equation and we plug in the chronologies for the full length that they existed to get the full reconstruction. So this is what the full reconstruction of Lee's Ferry flow looks like. It's from 1490 to 1997. Again, the light lines are the annual values. The darker blue line is a smooth filter to give you a better idea of the patterns. And here's the gauge record down here. So again, we can see the major features of the gauge record, this period of high flow, 1930s drought, 1950s drought. We can see these features in the reconstruction. There's that period of high flow. There's the 1950s drought. And we can see, again, this is not new. This is what Stockton and Jacoby saw in the reconstructions that have been generated since Stockton and Jacoby. This wet period is fairly anomalous. We go back to this period of time, we see maybe more extreme high flows, but nothing quite as persistent. In terms of the 1950s drought, that's a fairly moderate drought in the context of this full reconstruction. And then here's that new reconstruction in blue compared to Stockton and Jacoby's in the dark line, and one of the other reconstructions from Hidalgo et al. In brown, and the gauge record here. And you can see, well, there certainly are differences, but they're all showing the same general ups and downs. They're all showing this wet period in the context of the other sort of competing wet period in the early 1600s. They're showing periods of drought in the past that were more severe than anything we've seen in the 20th century. So it's a pretty robust result. Using all of these, we're using different methodologies in terms of the statistical approaches, the treatment of the data, and our reconstruction using completely different data for from the tree rings. So we can analyze this reconstruction in a little more detail to give you a little more of an idea of some of the characteristics of the reconstruction compared to the gauge period. I'm going to show you some comparisons with respect to high and low flows, duration and frequency of droughts, sequences of wet and dry years, and then patterns of wet and dry periods over decadal timescales, so smoothing the series and looking at them. So in terms of extreme high and low flows, I don't know if you've ever seen a diagram like this, but these are called box and whisker plots. And the whiskers, in this case, are the maximum and minimum values. The box represents where the 75th and 25th percentiles of the values fall. And this is for the full reconstruction and for the period of the gauge record. And you can see right off that the maximum and minimum values are much more extreme in the full reconstruction than they are in the gauge period, and the means and the medians are somewhat lower. Especially these minimum values are much lower in the full reconstruction. In terms of drought, here I'm defining drought. Drought can be defined in a number of different ways, but I'm defining it as one or more consecutive years below the long-term median. And then I'm assessing the number of single years, 2 years in a row, 3 years in a row, and so on, And then, so we've got the duration of these years below the median and the number of events. So as you can imagine, we've had the most of these single-year events, 2-year events, and then getting fewer and fewer as these consecutive years of below median flow are seen. So we have about 5-year periods, one each of a 6-year, 8-year, and 11-year in a row periods of below median flow. And then here's just the 20th century part of that record, 20th century only going up to 1997. And you can see that chunk of this full reconstruction is just a subset of what we're seeing in that longer reconstruction, which is what we might expect given this is only less than 100 years and this is 500 years. And then yet another way of looking at the same reconstruction. This is looking at flow categorized by percentile. So each one of these rectangles is a year of flow, and then they're categorized by percentiles of flow. So the blue values are the wet years, the orange and the red are the dry years, and then those that are marked with a red dot are the 10% driest years in the record. So if we look at the 20th century, we can see, just looking at these very dry years, we can see we have 5 events. 2002 would have been in that category as well. In comparison, if we look at the 19th century, we see we have 14 of these events, including 3 in a row. So very different pattern. This 3 in a row, very dry years, was actually preceded by some extremely wet years. So that certainly would have filled reservoirs if we had the reservoir system at that point. If we go back in prior centuries, we can see other patterns. Here we have, I think, 10 of these extreme events, 8 of them, and then back to 15, but 14 or 15, but a very different pattern than the 19th century sort of distributed extremes. And there are other things that you can look at here, like you can look at periods of time where there were maybe no extreme droughts, but really no wet years. And all of these patterns can make a difference in resource management. The sequences of flows from this record are actually being used by the Bureau of Reclamation in some of their work with the environmental impacts statement they're working on right now. So we see a very, very rich variety of sequences of flows when we look beyond just the 20th century. And then one final way to look at this reconstruction is in terms of low frequency variability. So I've smoothed the reconstruction with a 20-year moving average, and then what I've done is listed the 5 wettest and driest non-overlapping 20-year periods. So for the wet periods, it turns out in terms of 20-year averages, the 1602 to 1621 was the wettest, followed by 1905 to 1924, the compact period. If you average this in 20-year averages instead of 20-year averages, this period tends to be the wettest. So these two are pretty comparable. And then we also have in the top 5 another period in the 20th century, 1978 to 1997 here. So 2 of the top 5 ranking wet periods are in the 20th century. In contrast, the driest, we've got 2 of these periods in the 1500s, 2 in the 1600s, 1 in the 1800s, and you have to go to number 8 to find the dry period in the 20th century, 1953 to 1972. So when we look at the reconstruction this way, it appears that the 20th century may have been more wet than it was dry, looking at, again, these long-term periods of averaged flow over 20-year periods. So what about streamflow reconstructions going back further in time? We saw a little bit of a preview of what I'm going to show you from Jerry Zimmerman's presentation yesterday. But you're probably wondering, well, how do you get tree rings back to 762? The oldest living trees that we sample in western Colorado in the Front Range are about 800 years old. We have a few trees dating back into the 1200s, and even I think we have a tree dating back into the 1100s, living trees. So to get further back in time, we have to go out and sample what we call remnant material, and that's stumps and logs and little bits of wood that are lying around in the forest. And invariably, when you wander around in the forest, you don't usually notice these little bits and pieces, but they're all over the place. And in western Colorado and throughout the southwestern United States, these little bits and pieces of wood can remain in the landscape for hundreds of years. We've sampled little chunks of wood that look like the trees probably stopped growing 800 years ago and have inside dates. So the trees started growing. I think our earliest date is AD 210. So we can really extend our records back in time by sampling a lot of this remnant material, and then cross-dating, matching the ring with patterns with these samples that we don't know the dates of, with the living tree samples that we do know the dates on. And in that way we can extend our living tree chronologies back in time multiple centuries. So we've done that. Dave Miko collected a number of these remnant chronologies from where we had living chronologies in the San Juan area and the Green River Basin, and I did some collections in the Upper Colorado, and we pooled our resources, and Dave recently has submitted a paper that shows this extended record of streamflow for Lee's Ferry. This is the same reconstruction that Jerry Zimmerman showed yesterday. So it goes back to 762 and up to 2002. He's showing you, this is a 25-year moving average. The record that we're just looking at ended in 1490, so this is the part of the record we were just looking at. And here's the new part of the record, and you can see that the character of this record is a little bit different, particularly this period of time where we see this very severe extended period of drought. I think there were 62 years in a row below the average flow. This period of drought is not as severe, but it's quite persistent. And then this period of time here, you don't really have any very extreme high flows. This period of time is interesting. There have been a lot of studies with using different kinds of proxy data that have seen what we're seeing here, a period of extended aridity. There was a paper done by Cook et al. In which they reconstructed a gridded network of the Palmer Drought Severity Index with tree rings. So that's the Palmer Drought Severity Index. The PDSI is a reconstruction of a drought index. And what they did is they averaged together the grid points in this area, which they called the West, and then from that calculated a drought area index, the number of grid points that were under drought for each year from 8,800 through 2003. And this is a smooth record of that time series of the drought area index. And you can see here the average from about 850 to 1,300 was quite a bit higher in terms of the area under drought than the long-term average, and certainly higher than we see in the 20th century. This period of time has been variously called the medieval climate anomaly, the medieval warm period, which is actually, this period comes up as being warmer in the Atlantic, in Europe. In Western North America, it's looking like this period was characterized by dryness and aridity, and not particular droughts, but overall period of aridity. There's quite a few efforts now that are looking at this period and trying to determine what it was that caused this aridity. The external forcings on the climate of the Earth, the solar radiation, the amount of solar radiation that was reaching the Earth at this time was really no different than it is now. So our external forcing mechanisms are not different, indicating that perhaps this kind of a period of aridity could happen in the future. But people are trying to understand what it was that drove this period of aridity, if it was changes in sea surface temperatures in the Pacific or what. So there's certainly an area of research right now to try to determine what caused this period of aridity. So what are the implications of this record? I've shown you multiple Colorado River reconstructions that confirm that the compact was indeed based on an unusually wet period in the context of at least 400 years. These records also confirm that droughts can be more persistent and more severe than those that have occurred in the past 100 years. Some of the work that Dave Miko and I did with Steve Gray in a recent paper documented or looked at the recent drought, we called the recent drought 2000 to 2004, and evaluated that in the context of the Lee's Ferry flow, and found that we have to go back 150 years to find a drought that might have been worse. So it was a pretty unusual drought, but certainly not unprecedented. And then we also see this greater range of variability of high and low flows that has occurred, as well as a richer sequence of year-to-year flows. So then, well, that's all well and good, but how relevant is this record of the past to future conditions? These are instrumental records of Upper Colorado River Basin temperature from 1895 to 2005. This is annual temperature, and this is annual precipitation. And for temperature, we can see sort of a bumpy time series, but generally trending up, warmer conditions, especially since 1970. For precipitation, we don't see any clear trends, just a lot of variability. As Nicholas will talk about next, the climate models are predicting this trend to increase. So we're looking at increasing warming, that as the recent IPCC report is supporting, this is almost certainly due to human activities. So given that, how relevant is the record of the past to the future? Well, it's a good question. The climate of the past is unlikely to be like the climate of the future because we have these human activities that are having an impact on climate that they didn't have a couple hundred years ago. However, natural variability, particularly natural variability in terms of moisture, precipitation, and related stream flow, is likely to continue underlying this human-induced climate change. And it's particularly important at the longer time scales for understanding what's controlling things like drought, this period of aridity back in the medieval time period. If we could understand the controls on that, that information is important for looking into the future and perhaps predicting when we might run into a similar period. The range of hydroclimatic variability is projected to increase in many of these models, and we see that in the paleo record we do have an increased range of variability, so that record may be a useful analog for future variability as well. So in summary, a broader range of hydroclimatic variability than experienced over the past century in combination with these increased temperatures and also in combination with the increased demand that we've been hearing about will present challenges to the management of the Colorado River resources. We've heard a great deal about the resilience and the flexibility of the Colorado River and the law of the river, and many have argued that, well, it's resilient enough to carry us through these changes. But certainly the law of the river and the compact will be tested in coming years because of these changes. Thank you very much. Okay, I guess I have a few minutes for questions if anybody has them.
How should we think about the mean flow for that Stockton and Jacoby down at 13.5 acre feet? Is it just superseded by better procedures and much more data?
No, it's actually a little more complicated than that. The question was, well, Stockton and Jacoby's published long-term mean was 13.5 million acre feet. And there have been other reconstructions that show different long-term means. And the question was, how should we think about Stockton and Jacoby? Should we throw that out and go with the new figures or what? Actually, Stockton and Jacoby did 3 reconstructions that were published. And 13.5 was the one they selected. It was an average of 2, but they actually had quite a range of long-term means. And Hidalgo et al. Came up with quite a low long-term mean. Our long-term mean was a bit higher. We actually did 4 models, and we came up with something on the order of 14.8. So the question is, why are these means different? And that's actually something we're looking into. We used different training data. We used a different statistical approach. We used a different calibration period. We even used different gauge data. So we're right now looking at the cause for that change in mean. And I think we're sort of ruling out bits and pieces, but I think we'll be discovering how sensitive our treatment of the data is to that long-term mean in the next year or so.
Could you give us a feeling for the error bar around each year's estimate of the flow? In the sense that your calibration period is where you correlate ring width for different areas with the flow at Lee's Ferry. And so each point back in time is an uncertain estimate. Mm-hmm. And I don't have a feeling for whether the error around your line is only the width of the line, it's 3%, or is it 50%? Mm-hmm. Do you actually know that in 1600 a drought estimate is really different from a wet estimate? I mean, how big is the uncertainty in all of this?
That's a good question. The question was, how big is the uncertainty in the reconstruction? And again, that's a bit of a research question. Traditionally, we start with the error in the reconstruction model. So we can say, what's the error between the observed values and the gauge values? And we can assign a range of errors related to that that go back in time, and they're constant back in time. So they don't address how our estimates, the quality of our estimates might change going back in time. And there's a couple things that might affect that. First of all, our sample depth. As we go back in time, there are fewer older trees, so we have fewer trees, and there's potentially greater error. We try to control that by looking at the signal strength of the chronology as we go back in time, and we have a threshold for saying, well, there's too much variability within the chronology, we're going to cut it. So we try to control that. There's also some errors due to the way that we detrend the chronology, so this gets a little complicated. We've not figured a way to systematically consider all of those sources of uncertainty in our estimates, but we're trying things like ensemble reconstructions, where we're doing the reconstructions in a number of different ways based on different calibration periods, sets of data to see the spread that we have in the reconstructions going back in time based on different variables. So I don't have an easy answer to your question. It's something that we're looking at. We can talk more later if you have questions. The woman here. The question was, do the reconstructions of Streamflow reflect the Little Ice Age back in the, it was actually in the 1617 into the 1800s. That's true, it doesn't really reflect that. But again, we're looking at Streamflow. These are moisture-sensitive trees. The Little Ice Age signature was more related to temperature. So if we go to upper elevations and we sample trees at high elevations, those are the trees that are limited by temperature. And those are the trees that would reflect the cooler conditions in the Little Ice Age. So that's probably why we're not seeing it. The gentleman in the back.
Was there any, has anybody attempted to overlay any geologic kinds of activities during these periods of time, i.e. volcanoes and this type of thing that have influenced rather the environment,
Well, again, the question was, has anybody attempted to overlay other kinds of geologic evidence, like volcanic eruptions? And I think are you talking still about the Little Ice Age? Or just in general? In general. Well, actually, people have, but again, it's in reference to these temperature reconstructions, which the volcanic eruptions cause cooling. And so there are some, if you look at a temperature reconstruction for this area, you see cool temperatures, especially in the early 1800s, that seem to correspond very well to volcanic eruptions. In general, the temperatures are more sensitive to that kind of thing than the moisture variability, which may be affected, but we don't see a clear signature of that. This gentleman.
I assume that the data has been analyzed for patterns and have any patterns emerged whatsoever that have any predictive factors?
The question was, have the data been analyzed for any kind of patterns? And are you talking about like cycles and that kind of thing? Yeah. There's been quite a bit of work. Early decades ago, cycles were sort of in vogue, and the Turing data were analyzed for cyclicity, and it seemed like there was a 20-year periodicity coming up in these Turing data, and that's been readdressed multiple times as recently as the 1990s by Ed Cook. And indeed, there is a significant peak in about 20-year cycles, and of course people say, oh, sunspots, solar variability, and the big question is if that's the case, and actually if you analyze it, it looks like it might be a solar-lunar kind of cycle in the tree rings. If that's the case, then what's the connection between solar variability and drought in North America? And we haven't quite gotten the answer to that. People are looking at that. The other thing that's being done that's very interesting is work that's very, very new that's being done by Manu Lal, who's a hydrologist at Lamont Doherty at Columbia University, is looking at the spectral peaks in the reconstructions and using them to simulate stream flow or precipitation into the future. So trying to use the periodicities in the longer record as baseline predictors into the future, and that's really, really new cutting edge. In general, people say, well, can we use the tree rings to predict the future? And I say no. It's sort of like stocks. The future performance is no guarantee or past performance is no guarantee of future performance. But there's certainly lessons that we can take from the variability in the past, the long-term natural variability, that it's not going to stop with global warming. It's going to continue in the future, and understanding that is important, and it may contain some predictive ability. Way in the back.
I was a little surprised to not see bristlecone plots with your list of trees within their page. Are they not produced?
The question was, why have we not used bristlecone pine, which are very old? It's true, they are very old. They're the oldest trees that we've been able to date in the world. I think the oldest living tree is about 4,800 years old. So they're very valuable. They have a very, very valuable record. But these trees tend to be growing at upper tree line, and so they're not so sensitive to variations in moisture as they are temperature. And even the lower tree line bristlecone, which do tend to be somewhat moisture sensitive, the signal is not quite as strong as it is in these much lower elevation conifers. And bristlecone pine, although there's some in the Colorado Rockies in the upper basin, there's not a whole lot of them, and they tend to actually have a bit of a mixed signal. So they don't have as strong a moisture signal as the trees that we've been using. Time for more questions. You already asked one.
Is there any speculation on the cause of the few sort of major deviations in reconstruction lines that are otherwise quite tight to follow
Yeah, we're getting a sense for what some of the deviations are due to. Some of it's kind of complicated and has to do with the way that we treat the treeing data and how we treat them as predictors. So some of it's statistical. It's looking like, and this is something we're looking at right now, Dave Miko and I are working on this, could have to do with the selection of the treeing chronologies that were used. So we're actually looking into that right now.
maybe I didn't phrase that correctly, but I meant in the period that the leaf flow, Ferry flow, just the type.
Oh, during the gauge period? Okay, so I guess I didn't repeat the question. The question was, is there an explanation for the difference in the reconstructions during the gauge period? Well, I don't know exactly, but the fact of the matter is we've used different tree ring data, we've used different gauge data for the calibration, we've used different statistical techniques. All of those probably played a part in the differences. They're quite close, though. It's yeah. Okay, down here in the front.
Yes, this is about your methodology. How many tree cores, these little tiny samples, do you take? And is it 20, is it 100, or fewer than that? And then what happens about beetles or something getting into the tree and harming the tree as a result of your methods?
Okay, the question was how many tree cores do we use and what happens with the hole that results when we take the core out. We generally sample we take 2 cores out of a tree and sample about 20 trees per site. So we have about 40 cores per site. We generally in this study we're sampling all conifers, and conifers are really good at healing wounds. So once we take the core, the sap will fill that hole. We come back half an hour later, you can see sap coming out of that hole. So they're pretty good at healing themselves. Still have time for a few more questions here.
How well do the records of the Wind Rivers and the Front Range match?
Good question. I'm not sure that we've looked at that. We have in this study that the question. It was the reconstructions or the chronologies for the Uintas, the Wind Rivers, and the Front Range compare. In the study that we did recently with the reconstruction of Lee's Ferry, we also reconstructed flow in the Green River Basin and in the San Juan Basin and the main stem. The Green River Basin, I don't think we had any chronologies from the Tetons, but we might have had something in the edge of the Uintas. So I'm not answering your question exactly, but I'm answering it as well as I can based on the analysis we've done. We found that although there are differences between the 3 basins, in periods of extreme droughts, you tend to have drought all over the basin. We've done studies that have looked at streamflow reconstructions for the Upper Colorado and for the South Platte on the Front Range. And again, we find that although there's more of a difference during periods of extreme drought, you do have drought on both sides of the Continental Divide. So extreme droughts tend to be pretty widespread. Way in the back.
Is there anything that, and this is sort of outside of what you're saying, but is there anything that stands as a path? Should be like the path
So the question is there anything that says that we should expect the future to be like, the past to be like the future, or are we hearing that the future is going to be nothing like the past? Well, there's certainly people that take both sides of that question, but and there are modelers who say we should just look to the future and not to the past at all. And then you ask them, well, so what of the past is relevant? The past week, the past 30 years, the past 100 years, and they kind of waffle on that. But the fact of the matter is we do have long-term variability that is not going to shut off because we have human impacts on climate. I mean, it may be modified, it may be superimposed by warming, but it's going to continue to operate in some shape or form. So I think it's sort of a mixture of both. Some of the aspects of the future climate will not be like anything we've had, but certainly we'll have some underlying natural variability that will continue. And now I have to stop. So thank you very much.